Hi, it's Dr. Robin, aka Double O Pi. In this video, we're going to talk about setting up an Excel sheet for potentiometric titrations. This video is specifically made to help my Chem 242 students to help processing their data in labs 8 and 9. In this video, I'm going to walk you through making 3 different graphs: a basic titration graph, plus the first and second derivative graphs. And we're going to talk about how to use them to find your equivalence point. Now, just a note, the way we have these experiments set up at Northern is a little non-traditional, so if you attend a different school, you'll need to adjust this information slightly. I'll throw some cards into the video that will help you transform these instructions into something that works for a more traditional potentiometric titration. Let's get into Excel.
The first thing you need to do is you need to make a place to put your calibration curve. Now, I have put this basically down at the bottom of the sheet below my data. You could also put it on a separate tab right here. So basically you're going to put in the pH of the buffer and the millivolt reading that you got for that buffer. And then you're going to make a graph. So you're going to go to Insert. You're going to go to the scatter plots, and okay, so this is our calibration. So this person did not use a pH 2 buffer. We just have our 4, 7, and 10 pH. We're going to add a trend line, and what we want from this is we want the, let's get the options here. We want the equation and the r squared. I'm going to make that bigger so you can read it, or so I can read it. By the way, if you don't like that your pH values are right smack in the middle of your graph, you can change that. So what you're going to do is you're going to click on your y-axis and make sure you, when you're in the format axis thing, make sure that you go over to this part that looks like a bar graph, and you can see horizontal axis crosses. It's usually defaulted to automatic, but if you click on the axis value, you want the horizontal axis to cross at, let's say, minus 250. So it'll be down below your data points. And you can see that now all your pH values are down here. You don't have to do that. That's just something that it's nice to do. So I'm just gonna make my axis labels a little bigger, and I'm also gonna add some axis labels. And I do this because, remember, this chart should be printed out and put in your lab notebook, and you want to be able to look at it later and understand what it is you're looking at. So I always make sure I have axis labels on my stuff. All right, so what we have here is we have an equation, y equals minus 57.467x plus 382.53. Well, what does that mean? Remember, y is the millivolts and x is the pH, right? You see that right here with your axis titles. So the millivolts should equal minus 57.467 times the pH plus 382.53. So we're going to rearrange that so that if we have a millivolt value, we can solve for a pH value. So we're going to solve for x in terms of y. That would be this equation here, y minus 382.53 divided by negative 57.467 equals x. Okay, so that's your millivolt reading minus 382.53 divided by minus 57.467, and that will give you your pH reading. And so we need that because when you have your data, here's the increments that I added. Here's the millivolt reading. We're going to use that to convert our millivolts to pH. So again, our pH is going to equal Y, so that's our millivolt reading, minus 382.53. And let's put that in parentheses. Now we're going to divide that by minus 57.467, and that's our pH. Now that I have that formula in, I can just click and drag. I'm going to make it so that you can't see all the decimal places, so it looks neater. So now we have our pH. Here's the amount that I added. Of course, this is our starting reading, so we haven't added anything. But what we're going to do is to get the total volume added. Maybe you already did this in your lab notebook, but the easy way to do this is just with the formula equals this plus what we just added. So the next one is 500. Well, we could have done that in our head, but the nice thing about using the formula is that we could just drag that down, and now here's how much we added. Okay, so at this point we're going to make the graphs. And the first graph is going to be just the regular titration graph. And the titration graph always has pH on the y-axis and the total volume added on the x-axis. So as you can see, the pH and the total volume added are not right next to each other, so we have to just put in a scatter plot with no data, and then we're going to select data. And again, most of you are probably using Windows. Your data window is going to look slightly different, but what you want to do is you want to add a series. Okay. And then you're going to select your x values and your y values. Again, your x value is always going to be total volume added, and your y values are going to be pH. So this is our titration graph. Now, again, I'm just quick going to add my axis titles. So this is my pH, and this is my volume added. And by the way, volume added is in microliters. That's really important to know. I'm just making these readable. I know some of you can read stuff this small. I can't. I need my reading glasses otherwise. Okay, so here's our titration graph. Now, if you look at what's happening here, again, we have the pH on the y-axis. So we're seeing our pH increase pretty gradually, and then all of a sudden it just pops up. And right in the middle of this big change in pH is where our equivalence point is. So we can estimate, if you look at where the big pop-up starts, it's right at, I'm going to hover over this point here, I think, and this is 0.9000, 6.19. So it's starting about pH 6.19, and then this is where it slows down. It's ending at about pH 10.68. So halfway in between that would be 8 point something, 8.4. And you can see that would be like right about here where we don't have a point. So we can kind of estimate that it's the actual equivalence point is going to be somewhere between these 2 points. It's not ideal. So it's going to be somewhere between 9350 microliters added and 9450. So you could choose one of these. This one looks like it's slightly closer, or you might maybe want to do it halfway in between. We're going to make 2 more graphs, and essentially what we're doing is we're going to be doing a bit of not quite calculus. What we are looking for is where the pH is changing the fastest. And for those of you who have taken calculus, you know that the way you look for that is you look at the rate of change, the derivative is the calculus term, and you see where that's maximum. So what we're going to do is we're going to find the rate of change, and you can also think of that as the slope. And so we're not going to do any actual calculus, but what we are going to do is we're going to look at the instantaneous rate of change for every point. And the way we're going to do that is we're going to say, how much does the pH change with each change in volume? So that is essentially the change in y over the change in x, just like you used to do with lines in algebra. So this is your change in pH, delta pH. So for each thing, we're going to look at how much it changed. Now, for your first point, you can't do that. It hasn't changed because that's the starting point. So we're just going to not do anything here. And you don't have to do this. I'm just going to shade that in to remind myself that I can't calculate that. So we go down to the next one. How much did the pH change? Well, it's just going to be this minus that. Okay? And if you put in your formula correctly, you should just be able to click and drag. If you look at the change in pH, you can see that here is definitely the largest number, but we're not just looking for the change in pH. We're not just looking for the change in y. We're looking for the change in y divided by the change in x. And so that's delta pH divided by delta V. Delta V is how much volume did I add for this specific step. What is that number? Well, that's the volume added. That's the amount you actually pipetted in. I'm putting this here to remind you that this column right here is delta V. Okay, so now what we're going to do for this column right here, delta pH divided by delta V, we're just going to hit your equals because it's a formula. Equals now this cell for delta pH divided by, click on the matching volume added one, the delta V, and that will give you a number. And then we can click and drag that one. I'm going to slide this titration graph off to the side, and I'm going to make another graph here. And so basically, the thing that we call the first derivative graph is basically a graph of how does the slope change. That's going to be this column right here, as you add more NaOH to the solution. So let's go ahead and, again, we're just not going to highlight any data. We're just going to go to make our scatter plot with no data, and we're going to select the data for the scatter plot. Again, you want to add a series, which I know looks very different on a Windows machine. So this is going to be our first derivative graph. Okay, so our x values, again, will be the total volume added. That's going to be true for all three graphs. And then the y is going to be this column. You know, normally I say use a scatter plot, but in this case, you might actually want to connect it with lines. So there you go. So now you can see a little better what is happening here. You can see that it goes up to this peak and then it drops off. So this peak, again, represents where the slope is changing the most. Let me quick pop in the axis titles. And then what I'm going to do, I'm going to take the titration graph, I'm going to move it down here, just so we can kind of line it up. Let's make sure, yeah, this looks like it's about lined up. So now you could see how the slope is very small in this area, and then the slope gets much bigger, and then the slope actually drops down again, and becomes very, very small again. If you look at where this point is, you can see that our peak slope is at 9,450 microliters. And remember, when we were looking at this, we thought that the equivalence point might be somewhere between 9,350 and 9,450, but closer to 9,350. And this tells us that no, we actually are closer to 9,450. Okay, so now we're going to do one more graph. I'm going to slide this off to the side. I'm going to move this down here. And I'll slide it over. And we're going to make one more column. So this is the first. We looked at the slope of our titration graph. But now what we're going to do, we're going to look at the slope of this graph. And so what we have to do is we have to look at the change in y for this graph, which would be the change in this, and divide by the change in this. So what we're going to do is we're going to calculate the change in this. Now remember, we didn't have anything for the first one, there was no change, but that is also going to hold true right here. So there's no change here because that's the first point, so we're not going to calculate that. So what I've done here is I've said, what is the change in this thing? So that's why there's two deltas. And I'm going to calculate this exactly the same way that I did before. So I'm going to take, for the second point minus this. Okay, and you can see it's really small. And we're just going to do click and drag that down. And then we need to do this divided by delta V. Okay, so this column divided by delta V, which again is this one right here. Okay, so you're going to get really tiny numbers for this. And again, just going to... So now what we're going to do is we're going to click and drag. And now what we're going to do is we're going to make a graph. So insert a scatter plot. Again, don't highlight things. We're just going to select the data. So select the data, add a data series. The X is going to be these. The Y is going to be these. I actually take that back. Yeah, we do for these, it does really help to do a scatter plot where you're connecting the lines, because then you can see what happens. So this is our, we call it the second derivative graph. Second derivative would actually be if we did an infinite number of data points, but okay. What does this mean? If you look at this, the slope here is very small, and then it gets really big, and then it's increasing really fast, and then it decreases really fast, which means that your slope becomes negative. Okay, and where does it change from very positive to very negative? Right here at this point, which we say represents the inflection point. And so the slope here, when we're looking at the second derivative graph, we're looking for the point where you go from very big to very small, and that's going to be basically right where this crosses the x-axis. So if you look at this, this is 9450, this is 9550, and it's going to be right in between those two. So that gives you an idea. We're sort of fine-tuning what could happen if we had an infinite number of data points. Now there is another way to do this, which is a little weird, and that's called a grand plot. We don't do grand plots in this lab, but that is a way to kind of graphically extrapolate where your equivalence point should be. So anyway, what you're going to do is you're going to pick a volume that corresponds to whatever you think is closest to your equivalence point. So I'm just going to say 9450. And you're going to say that is the volume of NaOH where I reached my equivalence point. And then you're going to use it to do your stoichiometry.